Hello everyone, welcome back to another math video. So this time I'm doing how do you know if two sets of vectors are linearly independent? So first let's talk about what does linearly independent mean. So this refers to having a set of vectors. Let's just say in 2D for now. This is the x-axis, this is the y-axis. So let's say like one vector goes that way and another one goes like that way. So in this case, these two vectors, are they linearly independent or dependent? So here, the kind of condition is basically, can you put them together to reach any other point, or every other point you should be able to reach with some linear combination of both of them, or just one of them. So in this case, let's just say, so it's kind of hard to prove, but basically here's the equation. So I guess it isn't that hard to prove, but here's basically the equation for what I'm talking about by when I say linear combination. So let's say this is V1 and this is V2. So linear combination would be like, for example, vector 3 equals A. A is a constant times V1, and then plus B. B is another constant times V2. So V3, you call that the linear combination of V1 and V2. Now, basically, let's think about, reaching every single point. So, oh, by the way, here, the constants kind of have a scaling effect. And by scaling, I mean making it longer, making it shorter. You can also even like multiply by a negative number. That would kind of turn it 180 degrees and make it go the other way. For example, V1, when you multiply by a negative number, it would go kind of like backwards. So you kind of like turn 180 degrees. All right, so that's linear combination. And the question of, can you reach every single other point? For these two, it seems like, I can reach, for example, this point by just going down a bit. And then, from the end point of V1. So I can go like that. Basically, anything kind of parallel I can reach. And then, V1 can kind of continue, and then I can still reach anything kind of in this entire area. Also above, because you can go the negative direction. So, also when V1 is negative, you can keep on going parallel, and then you can reach all those points and all these points. So it kind of seems like, we've covered basically the whole thing, the whole plane. So I'm going to take that as meaning we can reach every single point, and therefore these 2 points, or these 2 vectors, can be considered linearly independent. So what's the kind of general rule though? So we know that these 2 can actually do the job, but what about what if we had, for example, we had this vector V1, and then we had that vector V2, the 0 vector. In this case, can we reach every single point on the plane just by using these 2 vectors? So the answer is, well, let's try. So if we make V1 bigger, we can go like that. So we can go anywhere along there. And if we go the opposite direction, we can go anywhere there. So it's kind of like only on this line will it actually work. And V2, we can't really do anything with that because it's the 0 vector. It doesn't really go anywhere except for stay at the origin. And even if you add it to any multiple of v1, you're still stuck at wherever the multiple of v1 put you. So in this case, the answer is no. We cannot reach every single point on the plane, and therefore those two are linearly dependent. Now, I'm not sure if the zero vector is a special case, but I'm just going to assume that those two are dependent. All right. So now another question: what if we had that and that? So v1, v2 over here, and basically, let's just say that these have a 180-degree angle between them, or pi radians. So if we have that angle, well, can we reach every single point on the plane? The answer, well, I mean, if you make v1 bigger, you can go on to anywhere along that line, and then v2 you can go anywhere along that line. But negative v2 kind of just puts you on the trajectory of v1, and the vice versa for v1. So in this case, it kind of seems like we're still stuck on the line, and this is a big problem because they're actually multiples of each other, you could say. So when v1 equals a constant times v2, basically when they're kind of linearly reachable through multiplication, then in that case they are going to be linearly dependent. And of course, this begs the question, what happens if this isn't true? Is there some general rule? Well, let's say we turn v1 by even a little bit. Well, then we could actually reach every single point on the plane just by doing our positive negative adding thing. So this is the actual condition for linearly independent. Alright, so that's the rule. Now the final problem to end off this video. Let's say that you have v1 and v2. These are givens. They're independent, linearly independent. And now I'm going to show you a second pair of vectors. So v1 plus v2 and v1 plus 2v2. So the question is, are they independent? Alright, let's move this into the corner. Alright, so to answer this question, let's rely on our initial condition, which is that v1, this condition by the way, does not equal k times v2. Now, knowing this initial condition, if we could somehow, use these two vectors and put them into kind of this equation format, then it would check out. So let's begin with just having the simplistic assumption that they are, in fact, not equal. So in terms of, being multiples. So here, we have k multiplied because k is, the constant. And so if this is true, then we're all good. But if it's not true, then we're gonna have some trouble. So this is just some algebra, kind of like proofs, but you don't really know what you're proving. And again, the focus here is to get something that looks like this. In fact, exactly like this would be best. So, because that would mean, we turned this into that, meaning that our plugging in of these two vectors actually does give back the results of the initial condition, which is that they're independent. So, let's start by putting v1s and v2s on separate sides. So the reason we do that is because in the original one, v1 and v2 are on opposite sides. So perhaps when we put them on the same side, we'll find that there's some external constant that we can factor out possibly. So let's move v1 to the right. So we have kv1 minus v1, and then that is supposedly not equal to v2 minus 2k v2. Now I've done the distribution of k in my head, but that's basically what I did. Now we can actually factor out v2 and v1 on both sides, or one on their respective own sides. Alright, so we have v2 and it's multiplied by 1 minus 2k, and then that's supposedly not equal to k minus 1 times v1. Okay, so now we have v2 times this strange thing there. But what is that thing? That thing is actually 1 is a constant, 2 times k is still a constant. When you subtract two constants, you get a constant. So that's really v2 times a constant. Let's call it k2, since k is already used. And then on the right side, k minus 1, that's still a constant. So that's not equal to v1 times k3, let's call it. So now this is kind of starting to look familiar, right? So we have k2 on the left, k3 on the right. And now let's think about this again. This is kind of commonly used in differential equations, by the way. So we know that k2 is a constant. k3, what is that? That's also a constant. So we don't really care about the specific values that they take on. So it's really about just getting rid of as many things as possible. And in this case, we don't care about constants. So that means v2 does not equal, let's just move k2 to the other side. So k3 over k2 times v1. So this really does look familiar, right? But the problem is we have k3 over k2 instead of just k. But the problem is, or the fortunate thing is that k3 and k2 are both constants, meaning that this is really just a fourth constant, or just a constant. And now we do have basically the kind of same equation, except we do have the k4 on the v1 instead of the v2, but it's the same deal. You could have just done the other way around, but the result is the same. And now we establish, because we can reach this initial kind of theorem way of seeing how independence works, this initial formula, we convert the new vectors we got into the old format. That means we actually do have a pair of linearly independent vectors. So the answer is yes. Alright, thank you guys for watching, and see you guys next time.